Top 25 data engineer interview questions and answers. 1. What is data engineering and why is it important? Data engineering is a practice of designing, constructing, and managing data pipelines that collect, transform, and load data into target systems like warehouses, lakes, or streaming platforms. It ensures data is high quality, timely, and accessible to analysts and ML teams. It combines software engineering, database management, and ETL/ELT processes to enable data-driven decision-making. Data engineers are critical because they create the infrastructure and processes that allow organizations to harness data for insights, AI, and operations reliably, at scale, and with governance. 2. Explain ETL versus ELT. ETL, extract, transform, load, involves extracting raw data from sources, transforming it in a staging area to meet schema and quality requirements, and loading it into a data warehouse. ELT, extract, load, transform, first extracts and loads raw data into the target, then applies transformations using the target's compute engine. ELT leverages modern scalable storage and processing, whereas ETL offloads compute elsewhere. ELT simplifies loading and allows iterative transformation. Choose ETL when transform logic is complex or sensitive, and ELT when your warehouse or lakehouse can efficiently handle transformations at scale. 3. What is a data pipeline? A data pipeline is a set of automated processes and workflows that move data from sources to destinations, performing transformations and validations along the way. It may include extracting data from databases, APIs, or files, applying cleaning, aggregations, and enrichment, then loading results into warehouses, lakes, or streaming systems. Pipelines can be batch-oriented or real-time and rely on scheduling, monitoring, and error handling systems. Effective pipelines ensure data integrity, scalability, and observability. They often use frameworks like Apache Airflow, AWS Data Pipeline, or Apache NIFI. Robust pipelines are essential for production-grade analytics and ML workloads. 4. How do you ensure data quality in a pipeline? Ensuring data quality involves multiple checks. Schema validation using tools like JSON schema or AVRO, type enforcement, null or range checks, deduplication, and referential integrity validation. Use unit and integration tests, data contracts, and monitoring alerts to detect anomalies like spikes or drift. Implement checkpointing, lineage tracking, and idempotent operations to avoid duplicates and maintain consistency. Utilize tools such as Great Expectations or Deek for automated data quality testing. Include sampling and reconciliation dashboards. Regular audits, strong logging, and collaboration with stakeholders ensure reliable data and build trust in analytics and applications. 5. Describe star versus snowflake schemas. A star schema organizes data into a central fact table surrounded by denormalized dimension tables, each dimension linking directly to the fact. It's simple, fast for queries, and intuitive. A snowflake schema further normalizes dimensions into multiple related tables, reducing redundancy and improving storage but increasing complexity. Snowflake schemas can add join overhead and complicate SQL. Choose star when query performance and simplicity matter. Use Snowflake when dimensions are large, rapidly changing, or when normalization reduces maintenance. Both are typical in data warehouses, and understanding them ensures efficient modeling for analytics workloads. 6. What is partitioning and why is it used? Partitioning is dividing large tables into smaller physical segments based on a column such as date, region, or hash of a key. It improves query performance by pruning irrelevant partitions, speeds up data ingestion and backups, and enhances concurrency by reducing contention. Partitioning also helps manage data lifecycle, allowing efficient archival or deletion of old partitions. Common partition types are range, list, and hash. Platforms like Hive, Redshift, and BigQuery support partitioning. Effective partition strategy depends on data access patterns. Good partitioning balances query efficiency, maintenance, and storage management. 7. How do you optimize ETL jobs? Optimizing ETL jobs involves parallelizing processing with frameworks like Spark or Flink, using vectorized operations, and choosing the right data formats, like Parquet or ORC, with compression. Push-down filters to the data source limit data movement, and cache intermediate results. Employ incremental loading via change data capture to avoid full refreshes. Adjust resource allocation, memory, executors. Tune job parameters, shuffle partitions, and schedule during off-peak. Profile data and jobs to identify bottlenecks. Apply column pruning and predicate pushdown. Monitor and log metrics for duration and throughput. Continuous testing and refactoring maintain efficient and scalable ETL pipelines. 8. Explain change data capture, CDC. Change data capture captures and streams only the data that has changed, new, updated, or deleted, rather than full datasets. It typically reads database logs or triggers, detects changes, and propagates them to targets like data lakes, warehouses, or message queues. CDC enables near real-time data integration, reduces data movement, and improves latency. It supports incremental updates and avoids recomputing full loads. Tools include Debezium, Maxwell's Daemon, and commercial offerings like AWS DMS-CDC is crucial for event-driven architectures, real-time analytics, and replication scenarios. 9. What tools are common in data engineering? Popular tools include data orchestration platforms like Apache Airflow, Perfect, and Luigi, distributed processing engines such as Apache Spark, Flink, and Beam, message systems like Kafka and Pulsar, and ingestion frameworks like NIFI data storage options include data lakes, S3, GCS, warehouses, Redshift, Snowflake, BigQuery, and databases, Postgres, Cassandra. Schema registries like Confluent or Avro help maintain data models. For monitoring and quality, tools like Great Expectations, Datadog, and Prometheus are used. Understanding the ecosystem and interoperability between these components is key for scalable, resilient data infrastructure. 10. How do you handle late-arriving data? Handle late-arriving data by using watermarking strategies in streaming jobs to control how far to wait for delayed events. Implement windowing logic that tolerates lateness, often using event time windows and a late data buffer. You can log late events and trigger backfill or reprocessing pipelines. In batch scenarios, use partition keys based on date and rerun ingestion for prior partitions. Maintain idempotent loads to avoid duplicates. Document data SLAS and notify users when lateness occurs. This ensures downstream aggregations remain accurate and decisions are reliable despite data delays. 11. What is data lineage and why is it important? Data lineage tracks the origin, transformations, and destination of data throughout pipelines. It documents each step: source, derive, filter, transform, join, and load. Lineage enables debugging, troubleshooting, and understanding how data flows. It supports impact analysis when making changes to upstream systems. It improves governance by establishing accountability, regulatory compliance, and auditing. Tools like Apache Atlas, Open Lineage, and built-in features in data catalogs preserve lineage metadata. Incorporating lineage ensures transparency, fosters trust in data, and eases incident response in case of errors or compliance concerns. 12. Describe schema evolution strategies. Schema evolution handles changes to table structure, adding, modifying, or removing fields, without breaking consumers. Strategies include using data formats like Avro, Parquet, or Delta Lake that allow backward and forward compatibility. Maintain schema registry to govern changes. Use version migrations. Deploy changes gradually, support multiple schema versions during transition, and test consumers. Employ optional fields, default values, and deprecation policies. For streaming, coordinate producers and consumers to handle new schemas. Document changes and communicate among stakeholders. Good schema evolution prevents pipeline failures, reduces downtime, and supports agile data model iteration. 13. Compare batch vs streaming data processing. Batch processing handles large, finite datasets in scheduled intervals. It's suitable for heavy analytics, periodic reporting, and historical transformations where latency is minutes to hours. Streaming processes continuous, unbounded data in near real time using event-time semantics, windows, and stateful operators. It is ideal for real-time analytics, alerting, and user-facing applications. Streaming pipelines are more complex, They require handling out-of-order events, watermarking, and state management. Batch is easier to develop but less responsive. Choice depends on use cases. If low latency is critical, go streaming. Otherwise, batch offers simplicity and efficiency. 14. What is Apache Spark and why use it? Apache Spark is a distributed, in-memory cluster computing framework enabling fast batch and streaming data processing. It supports APIs in Scala, Java, Python, and R, offering SQL, data frame, and structured streaming abstractions. Spark scales horizontally, parallelizing work across thousands of nodes. It's efficient for ETL, machine learning pipelines, graph analytics, and interactive querying. With its Catalyst Optimizer and Tungsten memory management, performance is high. Users choose Spark for its versatility, ecosystem, MLlib, GraphX, and support across cloud environments. It's a cornerstone of modern data engineering due to its power and flexibility. 15. How do you secure sensitive data? Secure sensitive data by implementing encryption at rest and in transit using TLS and KMS or HSMS use RBAC and IAM policies to enforce least privileged access. Mask or tokenize PI within pipelines. Apply column-level encryption or vault integration. Audit access logs and integrate with SIEM tools. Use network isolation, e.g. VPCs, private endpoints. For streaming, ensure secure broker configurations and authentication. Ensure compliance with regulations like GDPR or HIPAA through classification, retention, and consent mechanisms. Regularly review permissions and rotate credentials. Data encryption, access control, and auditing uphold data privacy and regulatory compliance. 16. What is schema on read versus schema on write? Schema on write requires defining and enforcing the data schema before loading into storage, like in relational databases or data warehouses. It ensures data quality and structure upfront, but can slow ingestion. Schema on read delays schema application until query time, typical for data lakes. This adds flexibility for exploratory workloads and varied data, but can shift validation burden to consumers and reduce performance. Use schema on write where transactional consistency and performance are crucial. Use schema on read when agility and schema flexibility are needed. Many architectures combine both, ingest raw data, then transform into schema on write targets. 17. What is a data warehouse versus data lake? A data warehouse is a centralized, structured repository optimized for analytical queries. It mandates schema on write, enforces data quality, and offers fast, indexed access. Data lakes store raw, structured or unstructured data in its original format, often using schema on read. Lakes are flexible and cheap for large volumes, but require additional processing for analytics. Lake houses like Delta or Iceberg unify both, enabling ACID transactions, versioning, and performance. Warehouses suit fast BI dashboards and regulated reporting, while lakes are ideal for exploratory analytics and ML. A unified architecture often leverages a lake for ingestion and warehouse for consumption. 18. Explain data versioning and time travel. Data versioning tracks changes over time, so you can query historical states. Time travel allows querying past versions of a dataset. Systems like Delta Lake, Apache Iceberg, and Snowflake manage snapshots and commit logs. Versioning enables auditability, debugging, rollback after erroneous writes, and reproducible ML training. Time travel is used for point-in-time recovery and reprocessing. Implement versioning by storing metadata logs and Delta files. Manage retention policies. This capability is crucial for compliance, data integrity, and incremental backfills, a key feature of modern lakehouse architectures. 19. What is orchestration in data engineering? Orchestration involves managing and automating workflow execution, dependency tracking, and scheduling for data tasks. Tools like Apache Airflow, Perfect, and Luigi define directed acyclic graphs, DAGs, manage retry policies, handle failures, and send alerts. Orchestration coordinates ingestion, transformation, validation, and loading steps. It ensures dependencies run in correct order and resources are allocated properly. Observability and logging help monitor pipeline health. Orchestration enables repeatable, reliable workflows with version control and documentation. It's the backbone of production pipelines, ensuring tasks run reliably, errors are handled gracefully, and combined steps are synchronized across environments. 20. How do you monitor data pipelines? Monitor pipelines through metrics, logs, and health checks. Track job durations, success failure rates, and data volume per stage. Set alerts on threshold breaches, SLA violations, or data anomalies. Use dashboards in Grafana or Datadog and logs aggregated by ELK, CloudWatch, or Stackdriver. Monitor downstream data freshness and completeness. Incorporate data quality and linear tracking. Enable end-to-end tracing of records. Periodically run reconciliation jobs to compare expected vs actual data. Monitoring ensures prompt detection of issues, SLA compliance, and visibility into performance, which are vital for trust and operational excellence. 21. What is columnar storage and its benefits? Columnar storage organizes data by columns rather than rows. This improves query performance for analytical queries that access subsets of columns. It allows effective compression and encoding, reducing storage and I/O. Query engines can skip irrelevant columns and data segments, enabling faster scans. Data formats like Parquet, ORC, and Arrow utilize columnar storage, making them ideal for analytics workloads. While row storage is better for transactional operations, columnar is optimal for read-heavy, aggregative, or filtering queries. It's widely used in data warehouses and lakehouses for efficient, large-scale data processing. 22. How do you handle data skew? Data skew happens when certain keys or partitions contain disproportionate rows, causing performance bottlenecks. Strategies include salting keys, adding random prefixes to distribute load, or pre-aggregating heavily skewed keys. Use custom partitioners or sampling to identify skew. Repartition datasets in Spark to rebalance hot partitions. Use bucketing or range partitioning. Leverage adaptive query engines that auto-rebalance. Adjust join strategies. Broadcast small side for skew joins. Monitor task timing to detect skew. Handling skew ensures LUTs are well balanced, preventing slow tasks and improving job performance, cost efficiency, and cluster utilization. 23. What is eventual consistency? Eventual consistency is a model where updates propagate asynchronously across distributed systems, so immediate reads may return stale data. Over time, all replicas converge to the latest state. It trades strong consistency for availability and partition tolerance. Applications using distributed databases, caches, or replicas rely on it for performance and resilience. It's suitable when absolute real-time consistency isn't required, like analytics or logs. Designers must account for stale reads and resolve conflicts via techniques like version vectors. Understanding eventual consistency ensures data engineers design systems aligned to consistency guarantees and use cases. 24. How do you design a scalable data ingestion system? Design scalable ingestion by decoupling ingestion from processing using message queues like Kafka or PubSub. Use partition topics, auto-scaling consumer groups, and batch writes. Employ schema registry to enforce contracts. Choose appropriate transport, HTTP, streaming, file-based, based on volume. Use backpressure and checkpointing for fault tolerance. Optimize data formats, Parquet or Avro, compression, and batching. Use CDC for efficient updates. Monitor lag and throughput. Employ auto-scaling compute for peak loads. Maintain idempotency and checkpoint recovery. This ensures your system can handle growing volume, maintain performance, and remain resilient to failures. 25. What are common pitfalls in data engineering? Common pitfalls include neglecting data quality or lineage, leading to inaccurate analytics. Hard coding schemas or credentials makes pipelines brittle. Backfills without idempotency introduce duplicates. Ignoring monitoring causes unnoticed failures. Over-normalization or poor partitioning harm performance. Premature optimization wastes effort. Lack of documentation undermines maintainability. Overfitting to current workloads hinders future scalability. To avoid these, implement testing, strong modular design, automated alerts, and version control. Document everything and use frameworks. Use infrastructure as code. Adopt incremental growth and monitor usage. Awareness of these pitfalls ensures robust, reliable, and scalable data systems. By preparing well-structured answers to these questions, you'll show both technical expertise and thoughtful engineering. Good luck in your interview.